Assalamualaikum to all students. So for today, for this video, I will explain to you on chapter 2. Okay, we will move to the topic of topic 5 on batch distillation. Okay, so we already done on chapter topic 1 until 4. So in this video, I will explain to you on the batch distillation. Okay, so in batch distillation, so we have two types of distillation covered in this chapter, which is batch distillation and continuous distillation. For batch distillation, what is the difference between continuous? Okay, you can see here. Okay, this is a simple batch. We call it as batch distillation. Okay, so flash distillation is one of the example of batch distillation. Okay, so later on for this for batch distillation, we have two types of distillation. We have flash, and also we have a differential distillation. Okay, so this is just I want to show you what is the example or what is the difference between batch and continuous. Okay, for batch, it involves the production of vapor by boiling the liquid to be separated in a single stage and condensing the vapor. So the process is still the same as distillation, whereas if we have a liquid, so this will be the mixture. So the mixture will be heated up, okay, at certain temperature. It will heat up. So component, for example, if I have component A and B, okay, component A with low boiling point, so A will vaporize first. So the vaporization will occur, and the vapor that escape the flask, okay, it will be contact and it will be condensed. Okay, here we have a condenser. Okay, so the vapor will be condensed and the product will be collected. So in this batch distillation, so no liquid is allowed to return to the single stage still to contact the rising vapor. So the vapor that escape the flask, it will be directly condensed, and the liquid produced from the condensation process will not be returned into this funnel. Okay, so this is batch distillation. So if we which means this process doesn't have a reflux process. Okay, whereas for continuous distillation, it involves the returning of a portion of the condensate to the still. Okay, for example here, I think as I mentioned before, okay, in the previous topic, so for example, if we have a liquid or feed here, so the feed will contain component A and component B. So both components will be heat up. So the component with less boiling point will be vaporized first. Okay, so the vaporization of the feed, it will enter, it will exit the top of the column. Okay, it will be condensed, and the liquid will be returned back to the column. So this is what we call continuous process. Okay, so the liquid will continuously reflux into the column until we achieve the desired purity of product A and B. Okay, so this is what we call reflux. Okay, this is an example of batch distillation. So we will look into flash distillation first. Okay, we also call it as equilibrium distillation. Okay, so what is flash distillation? Flash distillation occurs in a single stage, okay, where the liquid mixture is partially vaporized. Okay, for example, here I have a feed stream. Okay, feed stream, so it will be heated, and when it has been heated, the liquid mixture from the feed is partially vaporized. Okay, so you can see here the feed will be partially vaporized and partially become a liquid. Okay, so the vapor is allowed to come to equilibrium. So the vapor is allowed to come to equilibrium means when the vapor accumulate, when the rate of condensation or the rate of vaporization is equal, we call it as equilibrium state. So the vapor is allowed to come to equilibrium state with the liquid, and the vapor and the liquid phases are separated. We separate vapor and we separate liquid accordingly. Okay, so it also mentioned here this process can also be done by batch or continuous, but this for this we will see this process as a batch process. Okay, so for this flash distillation, there are some terms that you should know. Okay, so feed stream here, so it will have a feed F. Okay, so this is for the usually for the flow rate. Okay, we denote as a F capital letter, SS, XF as the mole fraction. Okay, mole fraction, initial mole fraction of A in feed. Okay, for example, if in feed stream I have component A and B as a mixture, so component A is the desired component, which means I do not want B. So I just want to extract, or I just want to distillate A and I want to remove B. So XF means the mole fraction of A only. Okay, I will consider only A in this calculation, in this mass balance. Okay, so for the feed stream there will be F and XF. So for the top, it denoted by V as a vapor. So this will be the usually the flow rate also, and Y star is the mole fraction, equilibrium mole fraction A in vapor. Okay, whereas for the bottom product, it will be denoted by L is the flow rate, L, so which means component A as in liquid. Okay, so XF X star is the equilibrium mole fraction of A in the residual liquid. Okay, okay, for example, if I have here if you can see the mass balance here, if I can write for you, so this is F in, so in will be equal to out, so F will be in, this is in terms of mass. Okay, so F is equal to V plus L, so V plus L in the exit stream, so it will be out. So okay, in terms of mole, if I can write in terms of mole, so F in is F times with XF is equal to V times with the Y. Okay, mole fraction of A in liquid. I will put star because of we are considering the equilibrium state. So for L, I times with the X star. Okay, so this is more. This is mass fraction, and this is the mass balance for in terms of mass and in terms of mole. Okay. Okay, so I will continue the equation. So for example, if I want XF as the subject, so I will bring F to the other side. Okay, it will become V over F Y star plus L over F X star. Okay, so V over F, okay, I will change into F. Okay, so F is actually the portion of vapor, or the portion of feed that has been changed into vapor. So F is equal to V over F. Okay, vapor portion divided by how many feet is entering, which means this equation tells you that F is actually how much feet has become vapor, how many feet that has been vaporized. So that's why V over F is actually F capital small letter. Okay, so if I can change okay, next from V over F, if I plus with L over F, it is actually a feed. Okay, it will become 1. It will become a feed, F over F, or we write as 1. Okay, so vapor portion from the feed plus the liquid fraction from the feed, it will be equal to 1. Okay, it will be equal to 1. So I will rewrite this equation in terms of F and in terms of 1. Okay, here. So if I can write this equation, and so just now this one I change into the F, I denote it as F. Okay, so next I will change L over F into another form. Okay, which is, so V over F, this now is F, okay, plus L over F is equal to 1. So if I want to change L over F, okay, L over F is also equal to 1 minus F. Okay, so this equation and this equation I will put into this equation. So it will become XF is equal to V over F is F Y star plus L over F is 1 minus F X star. Okay. Okay, next I will change this equation. Okay, so I will put Y star as the subject. Okay, Y is equal, it will be equal to XF, sorry, minus 1 minus F X star. So Y star is equal to XF divided by F minus 1 minus F over F. Okay, this equation also can be rewrite as, okay, so if I change F minus L, this one will become positive. So I will change this one, so it will become F minus 1 over F X star plus with XF over F. Okay, so this equation, you can see this, actually this equation is in form of Y is equal to mx plus C. Okay, so this is the M gradient, so this is the intercept C. Okay. Okay, next, okay, if you can still remember the VLE data, so vapor liquid equilibrium data, VLE data, if we have for distillation process, so we must know the VLE data for each mixture that we want to separate. Okay, so from the VLE data, we will form a curve here. Okay, for example, if I plot YA versus XA, okay, so I will get this, the purple curve as the equilibrium curve, okay, from the VLE data. So the VLE data will tell you the equilibrium composition of Y and also X. Okay. Okay, next, from the equation that we derived just now, okay, so this is 45-degree line. Okay, so from this graph, just now we have XF. Okay, remember XF, I have this is feed, this is XF, and this will be V and Y star, this is L and X star. Okay, so from the XF we can plot here. Okay, so we will touch on the 45-degree line. Okay, so if you can still remember the equation operating line that we derived just now, okay, is Y star is equal to F minus 1 over F X star plus XF over F. Okay, so this equation is actually, we will form a line here. The red line we call it as operating line. Okay, so when we have this equation from the operating line, we can find what is the equilibrium value for Y vapor. Okay, and we can also know the equilibrium value for X here. Okay, so for example, if I have the mixture of A plus B, for example, A is ethanol, B is water. I want to separate ethanol and water. I want ethanol as my focus component. Okay, so for ethanol and water system, they will provide you with the VLE data. So from the VLE data, I will construct the equilibrium curve, the purple one. Okay, so from the VLE data, I will get the equilibrium curve. Okay, next, for a certain question, okay, so F and XF and V Y star and L X star. Okay, for example, if I have, usually we will know the XF value, how many feed, how many portion of ethanol inside the feed. Okay, so how many mole fraction of ethanol inside the feed. So by using this XF, okay, so by using this XF, I will plot here. Okay, and I will touch at the 45-degree line. Okay, next, usually F will be provided. So when I have the F value, I will calculate from this equation, I will calculate the gradient, and also from the XF dengan F value just now, I can calculate for the C value, M and C value for the gradient and intercept. So I can draw a line. I can make a line by using this equation. Okay, next, okay, after I already get this line, so next I can find how the value for Y star and the value for X star, so that I can know how much ethanol exists in form of vapor in equilibrium, which is Y star, and I can know how much ethanol exists or exit as a liquid in equilibrium, which is X star. Okay, here and here. So this is the function of this graph and the function of this equation, so that you can know when the mixture we heat up, so we want to distillate, if the component already reach the equilibrium state. So I want to know how many mole fraction of the desired component in equilibrium, which is Y star and X star. Okay, so this is this is the purpose of the information from the operating line and the equilibrium curve. Okay, you can find the Y star and also the X star.